which will be given by Arthur Strauss from National University of Singapore. And the talk will be about reinforcement learning for real-time context-aware gate calibration with DGX Quantum. So looking forward to the presentation. Stage is yours. Please go ahead.
Is this on? Yes. Okay. Thank you very much for the introduction. It's a great pleasure to be here today and get a chance to present this work. My name is Arthur Strauss. I'm a PhD student at the National University of Singapore, and today I would like to do a very nice, based on the amazing background that was introduced by Morten a few minutes ago, it would be very easy to tell you about this story because it's a continuation of this endeavor of leveraging the core technology that enables the control of our qubits to a level that we hope we can get to make error correction even easier. So, the progress on quantum gates today are really outstanding. We finally reach a stage where error correction is tractable, and the primary condition for making this possible is essentially the idea that you can lower your physical error rates to a certain threshold, right? So once we get to that stage, we can wonder what can we do next, because obviously there are lots of challenges, and when we scale up, the physical error rates might not be also stable, in the sense that we might face emerging phenomenon, some kind of noise sources that you would not have expected if you didn't scale up. And so the main question is, how can we build better controls in such a way that those physical error rates remain stable with scalable systems? So, and an additional comment is that with every improvement you can do on the physical error rate, you can definitely, with the same qubits, do better codes. You can do better resource overhead management. And so we want to wonder, can we really get to the strategy with our control systems today to push the physical error rates even further? All right. So the kind of noise that we're trying to tackle is really the one that emerges when you are trying to do real thing on the quantum processors at scale. So when you have an idea of executing an algorithm, typically, we wanted to investigate a use case that, if you go only at the single qubit or the two qubit level, this is not necessarily something that you would imagine facing. So classical crosstalk is a very good example of this. So if you imagine you have this variational kind of ansatz on the left side, and you have parametric angles that define your single qubit gates. In the hardware in superconducting qubits, usually what it would amount to is that you play a drive on each individual qubit, which is proportional to the angle that you want to run, right? And so if you do Rabi driving, which is what you would like to do usually when you want to parallelize as much as possible, you will try to play this in parallel, and what happens is that if you have crosstalk, all of a sudden those angles will trigger a response, a coherent error in this case, on the neighbor qubit. And what's interesting about this noise model, although simplified, is that it already indicates that the circuit structure, so the set of angles we chose in this case, are defining the coherent error in a kind of unique manner. And so you can imagine that if I have classical crosstalk over many, many qubits, I will have this kind of crosstalk matrix represented by those gamma coefficients that you see here that will be directly dependent of the phi representation that we have set in our circuit. So the main question that we wanted to ask is, okay, there are many techniques that we can do to suppress coherent errors. So some will tell you do randomized compiling, some others will tell you perhaps you can try to make your way through dynamical decoupling. But usually the main issue is that you have to add additional gates, perhaps even errors when you try to do this, or you add an overhead in compilation, because if you do randomized compiling, you have to compile multiple versions of the same circuit, and this definitely takes time and resources on your control system. So instead, what we want to think about is, can we try to suppress, in real time, the coherent error contribution? And for that, we want to leverage the idea that, especially in superconducting qubits, when we have a fixed connectivity, you have building blocks that more or less will remain the same, and we want to open a degree of freedom on those 2-qubit gates that will remain stable. So now we switch from an original CNOT gate that had its own calibration based on what we collected at the characterization stage, and we want to fine-tune its parameterization, represented by this A vector that you see here. And so what it means at the pulse level is that although we still want to execute the CNOT gate, so the unitary we aim to achieve in the circuit is exactly matching the CNOT, its pulse level representation will try to capture a cancelling effect of the crosstalk issued by the previous layer, the one which is by essence dynamic in a sense. So here I'm really suggesting kind of a change of view of what we see as a quantum gate usually, right? Because we want to separate the abstraction between what the logical gate is supposed to do and its physical implementation. And its physical implementation can now be susceptible to modification based on the quantum circuit in which it's surrounded with. And so this entails kind of two main challenges. The first one is the building strategy, and I will show you how we use reinforcement learning and why we used it in a second. And there are the two constraints that we want to comply for this method. The first one is, by construction, the noise awareness. We should make sure that those A1, A2 parameters that we derive and so on are really reflecting the coherent error that is cumulated by the execution of the circuit. And at the same time, we want to avoid a model bias, because if you try to scale up, benchmarking this full crosstalk matrix will become very expensive, and we want to find a shortcut that will enable us only from measurement outcomes to find the right calibration stage. So instead of full characterization, then calibration, we propose a mapping that directly finds the right parameters you should get away for your specific application. But this is not the end of the story, because once you have found those A1, A2 parameters, you also have to wonder how you're going to store them in the memory of the control system. And that's not an easy problem, because if you think about very large fault-tolerant circuits at scale, if you start thinking about each individual instance being consisting of a waveform that is different, your control system will suddenly start to face very heavy constraints. So we want to find a way to overcome this constraint over here. And then, as alluded by Morten earlier, there is also the compilation overhead, which comes with the fact that you have to do training, which is why we saw in the previous talk that if you can embed things, the optimizer, into the FPGA, and you can rely on optimizing things on the fly, you avoid yourself the burden that was faced in the paper from Vlad Sivak at Yale in 2023 of applying reinforcement learning when you have lots of back and forth communications between the classical PC and the control system. And the dominant resource time is not so much the quantum execution, which in superconducting qubits will be of the order of microseconds, but really the compilation time and how many waveforms you have to upload in your control system. So again, the main idea is coming up with the technique and making sure that we can apply it without additional overhead, both in the training and in its execution. All right. So reinforcement learning, in a very brief manner, we are talking about something which sits between supervised and unsupervised learning, and it's an interaction between two entities. The agent, represented by this classical neural network on the left, in charge of addressing some actions. Actions mean, in our quantum context, circuit or pulse parameters you'd like to apply on your quantum system. The quantum system in the RL jargon is called the environment, and the objective is that the agent should learn how to find a probability distribution, this pi theta that you see on the screen, that which is a probability distribution which will yield with high probability the right actions that enable us to prepare a target state or to calibrate a target gate that we have in mind. But now the key adding that we wanted to emphasize to face this context challenge is to give the network a representation of the circuit. So typically, if I looked at things at the local level in this circuit, I want to switch again to a local version. So I will transform this C0 into a parametric version now, from which I want to find dedicated pulse parameters that will be directly dependent on the circuits in which it's meant to be executed in. So in this case, we decided to give a representation of the angles of rotations that are present in the previous layer. And based on the noise model I briefly mentioned earlier, each phi component will yield its own set of coherent errors on the local qubits. And so the goal of the agent will be to find correlations, the mapping between an input phi and the actions that would yield a high fidelity. And so that's exactly what we did, and we trained the agent. And so the first cool realization is that indeed the agent is able to learn very fast those correlations. So what you see in machine learning is very popular is what we call the learning curve. So in reinforcement learning, we talk about the reward signal directly inferred from measurement outcomes, and we wanted to mimic the execution that we would have on real hardware. So we only gather like the statistics of measurement outcomes we would have collected by measuring different expectation values, for instance, on the hardware. And now the main thing is that we anticipate that the main budget, and so the main training time, is really going to be dominated by the shots time. So we got about 30 million shots to get this full curve converging. And the main question is, how can we make this learning efficient? So to just confirm, we wanted to, once we have the training, of course, we also want to validate our intuition. And so this violin plot that you see is comparing the performance of what we call the baseline, which means if we stuck to the original C0 parameters that didn't take into account this crosstalk context, what is the fidelity on the local subsystem that we would have measured if we didn't do anything else. So here we have a direct mapping which is going to be dependent of the phi value that we sampled. In our noise model, the bigger the phi value in terms of Euclidean norm, the bigger the noise and therefore the lower the infidelity. On the other hand, the orange plot shows you that the agent consistently manages to find some actions that compensate each crosstalk signature by each random phi that we sampled. All right, and so now in the last few minutes, I would just want to tell you about how we pursued something very similar to what Morten introduced, which is leveraging the core control technology and the FPGA-based processor to make this learning tractable and fast in the lab. So the starting point of this whole thing is, again, we have this neural network that we don't necessarily want to put on the FPGA just yet, and I'm happy to answer any questions if you, because we are also exploring ways to integrate this in the FPGA, but there's a core question of motivation over here. But now the key insight is as follows. In reinforcement learning, we don't need to send directly the parameters. The agent is not trying to optimize over the actions directly. What it tries to do instead is to evaluate the quality of the policy, namely the probability distribution, represented here as a Gaussian, that generates those actions. And so what we do is at each epoch of training, we are sending the policy parameters themselves. And then everything else happens on the FPGA, meaning that we are going to sample all those actions in real time using a Mueller-Box transform, and going to generate on the fly the pulse parameters that will directly impact the transformation of our circuit. And again, the circuit context as well can be mapped through this parameterization to real-time adjustable pulse parameters. So the communication latency is actually killed because most of the updates are done now in real time. And you can imagine that all the variants of the circuit I would have needed to do to benchmark my quantum circuit are actually done with control flow and parametric adjustments on the FPGA. The rest of the workflow is pretty similar. We send back the reward for further processing, we update the weights and biases of the network, and we do so iteratively until we converge. So we have started to do experimental demonstrations on that, and I encourage you to come see us at Quantum Machines booth, where I will be giving a demo of this working live at the Israeli Quantum Computing Center. And here we just wanted to showcase that the dynamic application of this reinforcement learning was useful, and now we are actively investigating how we can map this crosstalk matrix and learn correlations between different angles. And the circuit, the Qiskit circuit that you see over here, is the exact mapping of what is going on in hardware. So instead of compiling different versions of the same circuit, which is usually what you need to do when you want to compute multiple observables or when you do tomographic protocols, here we do that all on the, it is precompiled all on the FPGA with this control flow structure. Conclusion, I hope I convinced you that like the control system technology that we have today really opens doors for scalability at no additional overhead if we play things right. So we need to come up with better abstraction layers that enable us to really leverage the maximum of this technology and play it with additional algorithms inside. And for now, like what we are currently investigating is how to embed even more this strategy of context-aware calibration within error correction workflows. And the idea now would be, similarly to this Google paper that came out a few years ago, to use syndrome data that naturally comes out of error correction to influence the way we are changing the gate parameters at the pulse level. And this is a really exciting direction, and I'm happy to take it offline and answer questions if you have any on this. I would like to acknowledge my colleagues from the National University of Singapore, and especially Aniket from Oxford University, who made all the simulations run in a super fast time. So with that, I would thank you very much for your attention.
Thanks. Thanks, Arno, for telling us how to use reinforcement learning for using better calibration and for understanding better our devices. So please, the board is open for discussions and questions. Here's one. Johannes, can you just throw the cube to the second row?
Thank you. Very interesting talk. My question goes, or I would like to have your view regarding other mechanisms as machine learning. So, for example, supervised learning, unsupervised learning, or maybe large language models. Do you see that space for within your scope for integrating?
That's a great question, indeed. So for now, like what we did as an early demonstration was a neural network which is fully connected. So a really simple layer, because the input encoding of the circuits, so if I go back to this representation, was really easy to embed. So we have a variational layer which contains a few angles that you can give a straightforward input neuron to this observable. Now, we are thinking about extending this to more complex circuits. So one which carry structure that, for example, would involve different connectivity activities between the C nodes, and we really want to think about this network to learn correlations between arbitrary quantum circuits and the right set of actions. And so the plan for us is to really investigate how we could do graph neural networks, for example, to encode circuits encodings, and that will enable us to indeed train. And the main question is, how do we do it at scale? Because now, for now, I talked only about one gate at a time, and what we're investigating next is how we can do a multi-agent kind of thing. So you will have a big network representation that will try to act on the same circuit with different parameters, and we collect a bunch of rewards all over the place.
Thank you.
Is there a further question? There is one further question, Chris. Yep.
Thank you for the nice talk. How robust is the reinforcement learning strategies you're adopting in the presence of noise? Do you need to adapt it to include maybe more physics-motivated nodes in your graph or anything to get the most power out of it?
So on the reinforcement learning part, what is the reason why it was adopted in a few previous works and why we chose it as well is the fact that it does not rely necessarily on the description of a model. So by construction, it's supposedly model-free. Now, of course, you can ask the question about what kind of noise model can I hope to counteract, right? And usually the answer will largely depend on the action parameters that you decide to play in. So in this case, and for the purpose of not adding any overhead on the compilation, we do only some kind of optimal control or adjustments of the gate parameters, right? So in this manner, you can only hope to correct coherent noise, in a sense. If you wanted to do something a bit more longer term, like drift handling, for example, we would have to see if the action space could include dynamical decoupling sequences, some things like that. It could definitely be incorporated, and we're actually working on an architecture at the software level that can enable us to break things down. But for now, we are kind of limited by construction of the action space of the coherent noise.
So thanks again for the wonderful talk and for the questions are answered. So thanks.
Thank you very much.
For Arthur, and also a present for you.
Thank you.
Thanks a lot. And with that, we are